In this video, we'll be practicing how to predict the molecular geometry of molecules. For a quick refresher, check out my video titled Predicting Molecular Geometry Theory. The link will be in the description below. Now let's start. First we have silicon disulfide. So Si(S)2. First, let's draw the Lewis structure. Silicon has 4 valence electrons since it's in group 4, and sulfur has 6 valence electrons since it's in group 6 of the periodic table. Since we have 1 silicon and 2 sulfur, we have to account for 4 plus 2 times 6 electrons, which is just 4 plus 12, which is 16. So 16 valence electrons in total. Now let's connect the atoms together in a molecule. So starting with the central atom, silicon, let's draw its symbol. Right. We add 4 electrons around it, 1 on each side, 1 side at a time, because there are 4 valence electrons. And we know that silicon is our central atom because our central atom is usually the least electronegative atom. Since silicon is less electronegative than sulfur, we start with silicon. We connect our 2 sulfurs to silicon using covalent bonds, or a sharing of 2 electrons. So let's add 1 sulfur on each side of the silicon. Sulfur has 6 valence electrons, 1, 2, 3, 4, 5, and then 1 shared. Now let's connect our other sulfur to the other side. 1, 2, 3, 4. So now we have our Lewis structure. Finally, we add double and triple bonds to satisfy the octet rule, meaning 8 valence electrons around each atom. So we join each lone pair unpaired electron on the sulfurs to the unpaired electrons on the silicon to form covalent bonds. So we take this electron over here on this sulfur and join it to this unpaired electron on silicon, and then we take this unpaired electron on sulfur, and then we join it to this unpaired electron on silicon. So now our Lewis structure will look something like this. We have our sulfur, a double bonded to silicon, and then another sulfur double bonded to silicon, and then we have our 2 remaining lone pairs on each silicon. So now each atom has an octet. And if we count all the electrons, we have 16 electrons in total. So that part is good. Finally, if you want, you can draw bond lines for each pair of shared electrons, right? So if we were to replace each pair of shared electrons with a bond line, it will look something like this. So a double bond connected to the silicon, and then another double bond, and then our last sulfur on the right. And so also, for more accuracy, since we know that the steric number of each sulfur is 3, right? Because we know that the steric number is the number of pi bonds plus the number of lone pairs, each sulfur will have a trigonoplanar geometry, right? Trigonoplanar geometry. So the electron pair arrangement will be one in which each electron pair will have 120 degrees of separation between them in order to maximize the distances between them. So if we were to kind of redraw these, the lone pairs around each around each sulfur, right? Each pair of electrons wants to maximize the distance between each other, right? Right, so now we have our other sulfur, and then around each pair of electrons, there's going to be 120 degrees of separation. So this is a more accurate representation of the Lewis structure of silicon disulfide. And as you can see, there are 120 degrees of separation between each electron pair. Double and triple bonds count as one electron pair according to VSEPR theory and have only one sigma bond apiece. So for more information on this, check out the video titled Identifying Hybridization States Theory, and also check out the video titled Identifying Hybridization States Practice. The links will be in the description. So finally, let's determine the molecular geometry. To determine the molecular geometry, we have to look at the steric number of the central atom, which in this case is silicon. Since there are only two double bonds around silicon, it has a steric number of 2, right? Since it has 2 sigma bonds and no lone pairs, right? So the steric number for the central atom silicon is going to be 2 lone pairs plus 0 lone pairs. 2 sigma bonds plus 0 lone pairs is equal to 2. And since it has a steric number of 2, but before that, once again, double and triple bonds have 1 sigma bond each, and the rest are pi bonds. So the geometry is going to be linear, right, according to our chart over here. And also, since the molecule has the form of AB sub 2, we can determine that the molecule is linear in that way as well, if you prefer that way. So moving on. Moving on, we have silicon tetrachloride, right? And the symbol for that is going to be SiCl4, silicon tetrafluoride. First, let's draw the Lewis dot structure. Once again, silicon has 4 valence electrons and chlorine has 7. So we have 4 plus 4 times 7, right? 1 for each chlorine. That's going to be 4 plus 28, which is going to be 32 valence electrons to account for in total. So starting with our central atom, we know that silicon is the only atom that forms multiple bonds and that chlorine is extremely electronegative, right? Elements tend to increase in electronegativity as you move up and to the right on the periodic table. So therefore group 7 elements like chlorine, therefore being the rightmost period in the periodic table tend to be the most electronegative. Therefore, silicon is our central atom. So we draw the Lewis symbol for silicon. Silicon has 4 electrons surrounding it, 1 on each side. And then next we connect the 4 chlorines to the silicon using covalent bonds. So now let's go ahead and connect our chlorines. Here's 1 chlorine up here. Here is another chlorine to our left. Here's another chlorine down here at the bottom. And then here's 1 more chlorine on the right. 1 on each side of the silicon. So here's our Lewis structure. If you count up all the valence electrons, or all the electrons in total, we have a total of 32. So that matches up. So 32 in all. And we can then replace any shared electron pair with bond lines. So we can sort of redraw this this molecule like so, right? If you prefer it this way. Here is another chlorine, 1 more chlorine down here, and finally our last chlorine over here to the left. Okay, so now looking at the central atom, the steric number is going to be 4 because there are 4 sigma bonds and no lone pairs around the silicon. Right, so our steric number is going to be equal to 4 plus 0 equals 4, right? We have 4 sigma bonds because, as you remember, all single bonds are sigma bonds. Since we have 4 single bonds, we have 4 sigma bonds. And we have no lone pairs around the silicon, so 4 plus 0 equals 4. And so our geometry is going to be tetrahedral according to our chart. And so it will look like this in 3D space. So in 3D space, we would have our silicon right here in the middle. We would have 1 chlorine up here, another chlorine over here, 1 chlorine coming out of the page, like so, and then finally 1 last chlorine over here, right? And so between each silicon chlorine bond is going to be an angle of 109.5 degrees, right? And so that's going to be the geometry of silicon tetrachloride represented in 3D space, right? And so finally we have, next we have chloroform. Right, so let's go ahead and delete this. So next we have chloroform. Chloroform is going to be CHCl3. Once again, we want to first determine the Lewis structure of chloroform. So for that, we need to tally up all the valence electrons present in chloroform. So first we have carbon, which is in group 4, hydrogen in group 1, and chlorine in group 7. So there are a total of 4 valence electrons for the carbon, plus the 1 for the hydrogen, plus the 3 or the 7 for each of the 3 chlorines. That's going to be 4 plus 1 plus 21, which is going to be a total of 26 valence electrons in total. So starting with the least electronegative atom and the only atom able to form multiple bonds, which is the carbon, we draw the carbon in our center. So here's our carbon, and then here's 1 electron on each side of the carbon, for 4 in total. And then we connect our hydrogen atom and our chlorine atoms to the carbon using covalent bonds. So now let's go ahead and connect each of our 4 atoms to the carbon. Here's our other chlorine. Here's another chlorine. And then finally here's 1 more chlorine. Right, so here's our Lewis structure for chloroform. Chloroform has, our Lewis structure has 26 valence electrons, which matches up to what we stated earlier. So we're all good on that front. And now we draw our bond lines. So here's our carbon. Here's 1 chlorine over here. Here's another chlorine down here. 1 more chlorine. And then finally our hydrogen. Okay, cool. So now to determine the molecular geometry of chloroform, we have to look at the central atom, carbon. Carbon has a steric number of 4, right? Because we have 4 sigma bonds and no lone pairs, right? So our steric number is going to be 4 plus 0, which is just 4. And for that reason, our geometry is going to be tetrahedral. Tetrahedral. And so if you wanted to sort of represent our molecule in 3D space, it would look something like this. So similar to the molecule we drew earlier. Here's our carbon in the center. Here's our hydrogen up top. Here's 1 chlorine. Here is another chlorine, and this bond is coming out of the page. And here's another chlorine, and this bond is going into the page. Right? And between any 2 bonds, we have a distance separating them of 109.5 degrees. So that's going to be the molecular geometry of chloroform. As you can see, this molecule kind of looks like a tetrahedron, right? Which is why we say that it's has a tetrahedral geometry. Okay, so finally we have ethylene. Ethylene is C2H4. For the Lewis dot structure, we have 4 hydrogens and 2 carbons. So we know that carbon is in group 4, so that's going to be 2 times 4 for each carbon, and then we're going to add that to our 4 hydrogens. That's going to be 8 plus 4, which is going to be a total of 12 valence electrons in total. And so, starting with the central atom, even though hydrogen is slightly less electronegative than carbon, since it's a little bit higher on the periodic table, it can only form one bond. So we will choose our carbon atom as our central atom, since it is capable of forming more than one bond, right? It just makes more sense. So we join the multiple bond forming atoms together first. In this case, our carbons with a covalent bond. So let's take our 2 carbons, right? Let's join them together with a covalent bond. And then we draw the remaining valence electrons around each carbon. And then we join the hydrogens to the carbons, starting with the atom with more unpaired electrons. That's generally how we would do it, but however, since both carbons have an equal number of unpaired electrons, we add them one at a time to each carbon, right? So let's take 1 hydrogen, add it to this carbon. Let's take another hydrogen, add it to this carbon, and then we just do the same thing one at a time for each of our 4 hydrogens. Okay, so now in order to satisfy the octet rule for each carbon, since they both have 7 electrons each instead of 8, we take the unpaired electrons and share them between the carbons in a double bond, giving each carbon 8 electrons. So what we're going to do is we're going to take this carbon and we're going to take this carbon. We're going to take this unpaired electron on our left carbon, and we're going to take this unpaired electron on our right carbon, and then we're going to join them together and then form a double bond between both carbons. So now it's going to look something like this. Here's 1 carbon, here's a double bond between them, and then here are our hydrogen atoms bonded to our carbons. Right, so ethylene is going to look something like this. So now let's replace any shared electrons with bond lines. Right, so let's draw it down here. We're going to take that double bond and then draw 2 bond lines, and then we're going to leave, and then we're going to use bond lines for our carbon hydrogen bonds. Right, and so since the steric number of carbon is, well, the steric number of each carbon is 3, right? Because we have 3 sigma bonds and no lone pairs around each carbon, right? Because we know that double bonds count as 1 bond, since there's only 1 sigma bond within a double bond. The electron pair arrangement of each carbon is going to be trigonoplanar. Right, and because it's trigonoplanar, the bonding pairs around each carbon will orient themselves in a way such that there is 120 degrees of distance between each bond, right? So the ethylene molecule is going to orient itself in this way. Right, here's our double bond, here's 1 hydrogen bond, Here's another hydrogen bond. Here's one more carbon-hydrogen bond and our last carbon-hydrogen bond. And around each bond is going to be 120 degrees of space. Right, so and this is going to be trigonal planar. So that's going to do it for this video. With that being said, thank you for watching and have a great day.